Hi folks, this is the first video for lesson 4. So you should have already taken a look at question 1 and given a try at answering it. If you haven't, please stop the video and consider it on your own and then start up again. Okay, so let's take a look at what they're recalling. First of all, we saw that when dealing with polynomial functions, they can only change sign at an x-intercept. Okay, so in order to change from positive to negative or negative to positive, you had to cross the x-intercept, but of course didn't have to change sign. So if you had a 0 of order 2, it would actually just bump off the x-axis. It wouldn't actually change sign. But those were the only places where it might change sign. And since polynomials are easy to sketch once you factored them, you can just use a quick sketch of the polynomial to determine when it's positive or negative, and that was useful for solving inequalities. So stands to reason that determining when a rational expression might change sign might also be useful. Okay, so if you think back to the investigation we did, certainly a rational function could change sign at an x-intercept. So let me just draw some random rational function. Okay, and say this is our rational function, and you say, hey, there's an x-intercept and the function can change sign. Okay, you might also have a scenario where it just touches the x-axis and then goes back up. So again, while it might change sign at an x-axis, at an x-intercept, there's no guarantee that it has to. Okay, but hopefully you realize that, wait, there were other places where a function can change sign. Consider this vertical asymptote. To the left of that vertical asymptote, the function is always positive, but then to the right of that vertical asymptote, the function is negative. So here we start to realize that there's other places that something like a rational function can change sign at. But similar to x-intercepts, if you look at this vertical asymptote, it's positive on the left and positive on the right. So just because you have a vertical asymptote, it doesn't mean it has to change sign. Okay, so this means that when we're trying to determine when a rational function is positive and negative, it's not enough just to look at the x-intercepts. Okay, we now know that you have to look at the vertical asymptotes. But let's see what's happening at a vertical asymptote, because one of the things that polynomials had was they were what we called continuous functions. Okay, so they never had any breaks in them. That's why the only place it could ever change sign is when it actually crossed the x-axis at an x-intercept. Whereas here we have these breaks in the function. It's not continuous throughout all real numbers because there's a break. I have to lift my pencil off the paper to draw the rest of the function. Okay? So you may or may not have considered another way in which a rational function can have a break. What about at a hole? So say you've got a rational function, okay, and at some point it's got a hole. Well, doesn't change sign. You still have that break, but yet it doesn't change sign. But what if the hole was actually on the x-axis? Okay, and you had something like this. You realize, hey, it is possible that it can also change sign at a hole if the hole happens to be on the x-axis. So think about the word we use for a function that you can draw without lifting your pencil off the paper. We call that a continuous function. So when we have a break in a function, we call that a discontinuity. So we say it's discontinuous at this value here where we have a vertical asymptote. It's discontinuous at this x value where we have a hole. So now if we wanted to put everything all together, we realize that for a rational function, it can change sign either at an x-intercept, just like we had before with polynomials, but it can also change sign at a discontinuity. Okay, and the discontinuities that we're considering now are vertical asymptotes and holes. But keep in mind, it doesn't have to change sign when we have a vertical asymptote or a hole, but those are the only places where it might change sign. Okay, so if we put this all together, we can say that rational functions can only change sign, okay, at the zeros, as we had before, and at discontinuities. And when it comes to rational functions, the only discontinuities we find are vertical asymptotes and holes. Okay? But let's specify here that they don't have to change sign there. So they will not always change sign there. Okay, so that's the answer to our first question, is where can they change sign? Well, now we know that it can still be at the x-intercepts, but it might be at these discontinuities like vertical asymptotes at holes. Okay, this is where now we come to the second question. Can we just draw a quick sketch to determine the positive and negative values? So when we had a polynomial, you could easily, once you had the x-intercepts, the orders of the intercepts, and the end behavior, you draw a quick sketch and you can just read off the graph whether the function is positive or negative. Problem is, rational functions are not nearly as easy to draw. Okay, so we're going to have to come up with another way to determine where it's positive or negative. So we're going to stop this portion of the lesson now, and I want you to just give a quick think for a couple of minutes. Might there be some other way that we can fairly easily figure out where this function here, so we're going to work with that function, which notice is already in factored form, as our example to determine a way to easily figure out where a rational function is positive and negative. So give it a quick think, and we'll start up in a little bit.